complex numbers from a trigonomic standpoint is very similar to the way we look at complex numbers in algebra. So if you remember, complex numbers, when we're talking about the actual form, is a plus bi, where we have to remember that this is essentially saying you're going to take real plus the imaginary. Well, with that, we can graph it. And by graphing it, what we have to remember is that we have a real axis and we have the imaginary axis, and they relate to your x and y. So my x-axis is considered to be your real axis, whereas your y-axis is considered to be the imaginary. Now with this, what it means is that when we have the form a plus bi, we are actually creating a coordinate point, a and b. Okay? So the easiest way to explain that is with these examples. So if you look at this first one, notice I have 4 minus I. So this is in my complex form, which is what I want. 4 minus I is going to give me the point 4, negative 1. Since my complex point is going to be a comma b. And so if we look at this, a would be 4, b would be negative 1. Therefore, my point would go, say, over 4. So 1, 2, 3, 4. And it would go down negative 1. So it would be, say, roughly there at 4, negative 1. Now if we look at the second example here, notice I don't have any a terms. So in this case, I actually have the point 0, negative 2. So again, this would be going over x and y none, but we would go down 1, 2, and there would be your point. Okay? Now with this, we can also do what's called the absolute value of these complex numbers. So when we're looking at the absolute value, we're looking at the measure of the distance from 0. In this case, it is sometimes referred to as the modulus, i.e. the absolute value. Similar to what you would think of in algebra. So let's say, for example, we have this coordinate plane, and we have the point here, which is 0, 0. And we are going to travel out away from my origin and end. And we're going to end here at some a plus bi location. Furthermore, we are going to say that this angle here is theta. Well, we can calculate the distance from one point to the other. So to do that, we would look at your distance from the point 0, 0 to the point AB. Why? Because this is a plus bi. Okay? So here, what's going to happen is we can use the distance formula. So we can say distance is equal to the square root. And if you remember from algebra, that formula says x2 minus x1 squared plus y2 minus y1 squared. Well, if we say that my x2, y2 is the point AB and x1, y1 is 0, then here we would have that our distance is equal to the square root of a minus 0 squared plus b minus 0 squared, which is going to give us the square root of a plus b. So what does this actually mean? Well, it means that we have a formula we can look at. So we have what we call the modulus. Okay, so the absolute value of, say, z is going to be equal to the absolute value of a plus bi, which is going to be the same as the square root of a squared plus b squared. Now if you look very carefully, this seems to be very similar to Pythagorean's theorem. So one of the things to take note there is that that strong theorem has a way of kind of showing up in a lot of different places, and one of those places has to do with complex numbers. Now we call this magnitude. So here we can be asked to find the magnitude, say, of the following point. So again, what we would take out of this is that this gives us the point -5, -2. So to find the magnitude, which is going to be the absolute value, say, of z, we would simply plug it into our formula. So we know the formula says the magnitude is going to be the square root of a squared plus b squared. So here all I have to do, plug and chug. So my magnitude here is going to be -5 squared plus -2 squared. So in this case, we have -5 squared is going to be 25. -2 squared is 4. So the magnitude is the square root of 29. Now you always want to make sure that you reduce as far as you can go. So once you come up with a value, you would then try and see if you can reduce that down. However, the square root of 29 does not reduce any, so this would be your result. Okay. Now with this, we can expand into what's called trig notation. Okay, sometimes you might hear it referred to as polar notation, but it's trig notation, and so the idea is very similar to your magnitude. So first of all, let's say again we're going to start here at the point 0, 0, and we are going to travel some distance out here, and this is the point a plus bi. Okay. Well, what that tells us is that if we were to drop our vertical and if we were to trace our horizontal, we have a triangle here. So with that, what do we know? Well, we would know that this would be, say, the angle theta. My horizontal distance is obviously going to be a. My vertical distance is going to be b, which means my radius is your magnitude number. So again, what do we know? Well, we know that my magnitude is equal to, or my radius is equal to the magnitude of a plus bi, which is the same as the square root of a squared plus b squared. And my theta here would be the angle, which is sometimes referred to as the argument. Okay. So what do we actually know? Well, first of all, we can work this the same way we would say a proof. So the first thing that we know is that we could let z, which equals the absolute value of a plus bi, be the same as the magnitude, a squared plus b squared. The second thing that we could do is we could then use trig functions. So what do I mean by that? I mean we can use this triangle to rewrite things. So if I look at my angle, first thing that I note is I note that the sine of my angle, so the sine of whatever this angle is going to be b over z. The other thing to note is that the cosine then of my angle is going to be a over z. So last but not least, if we were to plug the trig into your complex formula, you are going to end up with z cosine of the angle plus z sine of the angle I. And we get that by looking very closely here. So you can see I have the sine of my angle equals b over z. So if I solve for b, multiply both sides by z, and that's how we get this right here. Now for the cosine of the angle, it's a over z. So again, if I solve for a, I get this here. So again, what do I have? I have a plus bi, and so that's what we've done here. So when we're looking at it, the formula that we have to use can be written in two ways. The first is we would have z cosine of the angle plus z sine of the angle I, which is going to be the same thing as z times cosine of the angle plus sine of the angle I. And this is the formula in either version that you need to make sure that you pay close attention to when we are talking about trig notation for complex numbers. Okay? Now again, as a reminder, my z is always going to be that magnitude formula, a squared plus b squared, take the square root. So let's go ahead and take a look at a couple of examples, okay, and the way that some of these problems might look. So first, we have to write a number in standard form. So there's a couple ways that we do that. So the first thing we're going to do is simplify the values. We're then going to simplify, and then we're going to rewrite in your standard form type notation and use that in order to change into trig notation. So we want to find the trig notation for these specific values here. So my first one is going to be the square root of 3 plus I. So the one thing that I want to look at is we need to look at, okay, this is going to be the same as a plus bi. So in looking at that, I know that a is equal to the square root of 3 and b is equal to 1. So if we use my little coordinate plane here, we can simply draw our triangle. So we are going to go right about like this, and we can draw it down, where we know that my angle is here. We know that my x distance is going to be the square root of 3. We know my y distance here is going to be 1, which means we have my z. Now in order to find z, we can simply plug what we know into our formula. So remember, we already know z is equal to the square root of a squared plus b squared. So here we're going to take the square root of the square root of 3 squared plus 1 squared. So here the square root of 3 squared is going to leave me with 3 plus 1, which is going to give me 2. 3 plus 1 is 4, square root of 4 is 2. So here we know that z is going to equal 2 because that's what we solved for. So we have a triangle we can work with. So that we also know that we have our trig notation, which says z times the cosine of the angle plus I sine of the angle. So I need my cosine and I need my sine. So to find that, I know that a is equal to z cosine of theta, and I know b is equal to z sine of theta. And I know my triangle here. So the first thing I need to look at is cosine and sine. So my cosine of my angle is going to be adjacent over hypotenuse. So square root 3 over 2. So in doing that, we need to be able to back calculate what that angle is. So the square root of 3 over 2, this tells me that my angle is going to be 30 degrees. Now I can double check that with my sine, and so here I've got the sine of my angle is equal to 1/2. Again, that tells me that my angle is the 30 degrees. So use one to calculate your angle, use the other to check to make sure that you did it right, and then all you simply have to do is plug your information into your formula here. So we know z was 2, so this is going to be 2. And then I've got the cosine of 30 degrees plus I sine of 30 degrees. And since all I want is the notation, I'm not asking you to simplify or solve. I'm asking for the notation that we use. So therefore, this right here would be the result that we are actually looking for, is the trig notation form of the square root of 3 plus I. Alright, let's do it one more time. So here I have -5 plus 5I. So again, I have to be able to look at what it is that I have. So here, if I look at it, this tells me a plus bi. So here my a is equal to -5. My b is equal to 5. So I can draw my triangle using my coordinate plane. And you want to make sure that you put that triangle in the proper spot. So a is the same as my x value, so I'm going to be here in my second quadrant. So here is my theta. So this is the -5. My y was positive, and this is my z. So I need to use my Pythagorean's theorem or my z formula to find my missing term. Remember, that's a squared plus b squared. Take the square root. So here this is going to be the square root of -5 squared plus 5 squared. So this is going to be 25 plus 25 gives me the square root of 50, which here is going to give me 5 square roots of 2, because you need to reduce this down as far as you can go. So here my z is equal to 5 square roots of 2. Again, now that you know your triangle, you can find your formula. So just like before, you need the cosine of your angle. So if I look, my cosine is going to be -5 over 5 square roots of 2. When I reduce this down, I'm going to end up with the negative square root of 2 over 2, which we know to be 45 degrees. I'm going to check it with my sine. Sine is going to be 5 over 5 square roots of 2. Again, that's going to reduce to the square root of 2 over 2, which is 45 degrees. Now, take a look at the negative sign and take a look at where we actually are in our quadrant. So knowing that this is 45 degrees, what we actually did here is we discovered the reference angle. So these are your reference. Because we're in quadrant 2, you need to remember your reference angle says I take 180 minus the reference. So to find my angle, I have to take 180 degrees minus your reference, which is going to be 180 minus your 45, So your angle here is going to be 135 degrees. Okay. Now the reason we did not have to do that in this first example is because this angle here that we found is in quadrant 1. And one thing that we know about quadrant 1 is that your angle equals your reference angle. Okay. However, in quadrant 2, it's that different story. So we have to actually find the angle here. Once we know it, now we can simply plug information in. So z was 5 square roots of 2. We're then going to have the cosine of 135 plus I sine of 135. Now the last thing that we can do with these, and I know, we're all tired, but we can go from standard notation or from trig notation and we can work backwards into what's called standard notation. So what we're doing here is, this means we want to go back to a plus bi form. That's our goal. So we have to use this knowledge here to work ourselves backwards. So first and foremost, I have the cosine of pi over 3. And when I evaluate that, it's going to give me 1/2. And then I also know that the sine of pi over 3 is going to give me root 3 over 2. Now, because both the cosine and the sine are positive, this tells us that you are in quadrant 1. So here, what we actually have is we have 5 times 1/2 plus the square root of 3 over 2i. But then, this is not fully a plus bi form because we've got this 5 on the outside. So you have to distribute your 5 through, which says that we have 5/2 plus 5 square roots of 3 over 2i. And that is your standard form. Alright, let's do it one more time. Here I've got the cosine of 135 degrees, which is going to give me negative square root of 2 over 2. I have the sine of 135 degrees, which gives me positive square root of 2 over 2. This right here tells us that we are in quadrant 2. So it's always a good idea to know what quadrant you are working in, so we can plug our information in. So this is going to be 4 times negative square root of 2 over 2 plus square root of 2 over 2i. Multiply the 4 into both sides, and we end up with negative 2 square roots of 2 plus 2 square roots of 2i. So that is everything that you would need to know to get started when working with the basics of doing trigonometry with complex notation or complex forms. So if you have any questions, please let me know. If you have any additional examples that you need to have worked out, let me know that too. I'd be more than happy to do that for you. Otherwise, I do hope you enjoyed yourself. I do hope you learned a lot, and I'll see you next time.